vector. This is also computation, but we also have like a definition of like all the things that we did here. So uh, okay. And then you should learn, given some matrix, you should learn to compute eigenvalues and uh, corresponding eigenvectors. So I'll do all one type of examples of each of these problems today, and then we will do some problems from the um practice midterm that I posted. So I also found a nice. I mean, for this course, we don't really need to learn that determinants are like a multilinear operator of top degree and stuff. But there is a nice notes that I found by Professor Karen Smith. She's one of like the leading figures in commutative algebra and stuff. Uh, she's in University of Michigan. So I posted that problem set in the canvas. If you want, you can do it. Um, it's not really important for the exam, like midterm or even the final, but you sort of get a good idea of what determinants are, not just the computational way, but really, and neither the geometric way also, but really the algebraic properties that makes it like an important thing in geometry. Okay. So let's start with the simplest thing, computing eigenvalues, eigenvectors of a matrix. This is where we stopped last time. So let me find an example. So let A be n cross n matrix. So the characteristic polynomial of A is given by determinant of A minus x times the identity equals to P of x. Or sometimes they write it as chi of, sorry, chi of A. Okay. So we have an n cross n matrix here. This is also another n cross n matrix. X is the unknown. We are just taking the determinant. That thing is called the characteristic polynomial of any matrix. If we started with a linear operator or linear map from Rn to Rn, so linear maps from same vector space to same vector space are also called operators. Okay, so I keep saying this without defining it. So linear maps when domain is same as target are called linear operators or just operators. Okay, so if you have an operator, then or a linear map from Rn to Rn, then you have without any, if you fix any basis, you have a matrix, and for that matrix you can define its characteristic polynomial. And this, like the zeros of the characteristic polynomial, doesn't change if you change the basis of t. So suppose there is a change of basis in t in here and in here, in here and in here, so that the A is transformed to something else. So for example, there is some P matrix and some Q matrix such that so this is the base change matrix here, then this is the base change matrix here, then you'll get suppose another new matrix A1. So this is some new matrix when you have changed the base for T. So this is also T with respect to some new basis. So one can show that the like the set of all characteristic polynomial of this thing, like the set of all zeros of the characteristic polynomial of A1 are same as the set of all zeros of the characteristic polynomial A. So okay, I mean um, okay, so let's do this. No, I meant to say this. Yeah, if you have a change of base like this, in that case, so in A1 you can do PAP inverse minus x times identity n. Then you can think of identity n as p times p inverse. So this becomes determinant of p a minus x times identity n p inverse. So so determinant has this property, the determinant of a b two matrices is equals to determinant of a times determinant of b. So you can apply that here and you will get now again if you apply the same property to uh, here, like same property means if you have p and p inverse as ab, then this is determinant of the identity which is 1. This you can break up into p and p inverse. So therefore you can say the determinant of p inverse, like divide both sides by determinant of p, is 1 divided by determinant of p. That is the inverse of this real number, determinant of p. So in other words, determinant of p times determinant of p inverse is 1. So this and this combined contribute just 1. So we get determinant of a minus x times identity n. So we proved that for similar matrices, these sort of things are called similar matrices. For them, the characteristic polynomial are same. So for similar matrices, that is A is A P inverse for some invertible P, the characteristic polynomials are the same. Okay, so this is one simple remark about characteristic polynomials, that if you have similar matrices, then you can do this. And yeah, anyway, I want to do this after the midterm, so I'll not go too much into it. But I guess I give set this up as a problem in the practice midterm, so I will do that. Okay, so let's compute. So okay, so then we are still in the middle of the definition when I started going off. So the zeros of characteristic polynomials of A are the eigenvalues of A. If lambda is an eigenvalue of A, there exists a non-zero V in Rn such that AV is equals to lambda V. Such a V is called an eigenvector of A associated with lambda. Okay, so let's compute eigenvalues, eigenvectors of this matrix. So we have 1, -7, -1, -2, -3, 2. So this is a typical upper triangular matrix, and you can sort of see it's very easy to compute. You basically okay, let me just do it without talking too much. So first we write, how do you compute? We first write down the characteristic polynomial. So this is a 3 cross 3 matrix, so this would be x times identity. Okay, so therefore we are computing the determinant of 1 minus x minus 7 minus 1, 0, 2 minus x minus 2, 0, 0, minus 3 minus x. Okay, now this is a pretty simple looking thing. You can still do the, anyway, the determinant is also pretty simple. If you want, you can still do the computation, but if you just observe, you can see that if you set x equals to 1, then this row, this column becomes 0. Therefore, what will happen is the determinant will be 0. So that means x equals to 1 is a solution, right? If you have a matrix with one column that is completely zero, then you can show that, see that easily, that I mean, for example, if you just express the determinant in using that column, then everything would be zero, right? So the determinant is zero. If you have so x equals to 1 should be one eigenvalue. Good. Now if you set x equals to 2, then you can see that this guy would be 0, and then this guy would be negative 1, right? So therefore this column negative 1 0 0 and this column negative 7 0 0, they are linearly dependent. So this is like just 7 times the first column, right? So again, if you have two linearly dependent columns, those again would be zero, because you can just row reduce and make one of the columns zero. And row reduction is a like a non-singular operation. So you are just multiplying with a non-singular matrix, so that doesn't change the sign of the determinant. I mean, zero non-zero of the determinant. So in this case, again, since we have two linearly independent columns, the determinant is again zero. And finally, again, if you see, if you subtract 3 from the matrix, so if you set x equals to 3 in here, in here, then again, this entire row becomes 0. So the determinant will again be 0. So you have like, this is a cubic polynomial with real entries, and you have three distinct candidates that would make the determinant 0. So therefore you have the roots. So if you want, you can just say it that way. Because this is an upper triangular matrix, like this matrix is of this nice form, the computation is very easy. It will not be so if you for different sort of matrices. Anyway, but so that is one way. Let us just follow the way we just know how to do determinants. That is also not hard if you just write down the definition. Bit more writing is all. So consider this, and then this is the associated determinant. Then if you have this thing, you will have minus times minus 7, and then determinant of this and this block, right? So 0 0 minus 2 minus 3 minus x, and then plus minus 1 times determinant of the rest of it, so this block. So that would be 0 0 2 minus x 0. Now notice that these are determinants. We are computing determinants of two matrices where one column is completely zero. So both of these guys would be zero. So it is really one thing. And again also this diagonal is zero. Therefore it is just a product. So 1 minus x, 2 minus x, minus 3 minus x. So eigenvalues are, so this is your characteristic polynomial. So when you are asked to compute determinants, your first step should be to compute the characteristic polynomial completely. Come until like here in like write the determinant of a minus x identity 3, explicitly compute it, and then say that this is our characteristic polynomial. Now we are going to look for the zeros of the characteristic polynomial. Those would be the eigenvalue. So the zeros are x equals to 1, 2, and negative 3, right? So these are the zeros. This is a cubic polynomial and these are the zeros. Okay, now I need to find an eigen vector for each of them. Okay, so first let's do it for lambda equals to 1, or maybe we should say x equals to 1. So if we have so if v is an eigenvector, say v1 in Rn, sorry, R3 in our case, is an eigenvector, then we will have AV equals to 1 times V, that is AV is just V. So that means we should also have A minus identity 3 V equals to 0, right? This is the element in Rn. So, and also you can directly say it from here. So therefore first let us write this 3 cross 3 determinant. So this is 0, then minus 1, then minus 4, and then minus 7, minus 1, minus 2, this times V1, V2, V3, right? So we need to make this thing 0, right? We need one such V. So that means we are basically solving this system of linear equations. So this is what? This is minus 7 V2 minus V3 equals to 0, minus V2 minus 2 V3 equals to 0, and minus 4 V3 equals to 0, right? So you can see that V1 is not present here, so it can be anything. V3 is forced to be 0, and because V3 is forced to be 0, V2 is also forced to be 0. So V2, V3 are 0, and you can set V1 to be anything. So let's set this as 1 for now, right? Then we have that A minus identity 3 times V is 0. So therefore, if you just choose 1, 0, 0, this is an eigenvector. And the eigenspace, that is, we discussed that uh, the eigenvectors constitute a linear subspace. So this that would be this linear subspace. We have no V1 doesn't show up in this homogeneous system of linear equations. So you can set V1 to be anything. It's a free variable sort of, and V2 and V3 are 0. So this is your eigenspace with respect to 1.
Wait, sir, I think the second number in the second row should be 1 instead of -1.
Oh, thanks. Okay. Yeah. I mean, it doesn't change anything.
Yeah.
Yeah. Okay. Right. And this is actually, in general, it is true. If you just start with a upper triangular matrix, I think we defined it. I don't know if we defined it. If you start with an upper triangular matrix, that is the block below the diagonal is 0. Only non-zero elements show up before on the diagonal or above it. Um, then you can show that the characteristic polynomial is always like this. And the reason is simple, because if you try to expand your determinant in terms of the top row, right, only this guy, like the determinant associated to this guy would potentially have anything non-zero. All the other guys right to it, right, they will always have to have this 0 column in them. So all the associated determinants, they will become 0, right? So if you have an upper triangular matrix, the characteristic polynomial is very simple, and computing the eigenvalues are very simple. I mean, if it is just this form, then you know the answers. Okay, so we have two more. So let's do for them. This is again 1 minus 7 minus 1, 2 minus 2 minus 3. Okay. And now we want to do it for x equals to 2. So now we are going to try to solve this system of linear equation, right, for some non-zero, and find some non-zero solution of this. So this matrix is minus 1 7 minus 1 0 minus 2 and minus 5. Okay, so we will have v1 plus 7v2 plus v3 equals to 0, and then we have 2v2 equals to 0 and 5v3 equals to 0. What happened? Oh, no, there is no v2, sorry. This is again v3, right? This is to v3 is 0, so you'll have v3 is 0, and because v3 is 0, you have the first equation, so you have v1 plus 7v2 equals to 0, so therefore you can say that v1 is equals to minus 7 v2. So the eigenspace, you can explicitly write it down. The eigenspace looks like minus 7 v2 v2 and 0, where v2 is a real number. And if you need explicitly one eigenvector, just set v2 to be something non-zero. So this is an eigenvector. Okay. And we also have minus 3. So for x equals to minus 3, can do a plus 3 times identity. We are going to solve this and find non-zero solutions. So this would be 4, negative 7, negative 1, 0, 5, negative 2, and triple 0. This times v1, v2, v3 equals to 0, right? So again, you see that the last column, we don't really have like 3 equations, we really have 2 equations, right? So we have 4v1, 7v2, v3 equals to 0, 5v2 minus 2v3 equals to 0. So okay, we can multiply the top guy by minus 2, then we will get this is negative 8v1 plus 14v2 plus 2v3, and if we add it with this, Then we get, okay, I mean, this is equivalent, but I think we learned row reduction, right? So let's do it in that cool way. So we will try to row reduce this matrix. I mean, you don't have to, however you like, you can do it, but let's do that. So multiply the second row by half and subtract from the first row. Then one gets 4, and we have like 2.5 here. So minus 9.5, and then this is 0, right? Then uh, okay, and I guess pretty much that is the best we can do. If we try to get rid of the middle thing, yeah, okay, this is fine. So 4v1 minus 9.5 v2 is equals to 0, and 5 v2 is equals to 2 v3. So that means we have v1 is equals to 9.5 by 4 v2, and v2 is equals to 2 by 5 v3. Therefore this guy is equals to this. So you have written v1 in terms of v3, v2 in terms of v3, and so the eigenspace is, we have, this is 2, I mean I can make it just 19 by 20, right? So let's do that. 19 by 20 v3, 2 by 5 v3, v3, v3 is some real number. Excuse me. Okay. So this is the eigenspace, and then we need one eigenvector. So you can set v3 to be 1 or something, or maybe let's set v3 to be 20. Then this is 19, 8, and 20. So this is an eigenvector associated to -3. Okay, so yeah, this is how you so the so to find the eigenvector, all we have to do is to solve this sort of systems. You can do it however you like, whatever seems easier, but do it correctly. And if there is a minor mistake in calculation, we will obviously have partial credit and stuff, but this is easy, so you should not miss points in this. Okay.
Wait, sorry, can you scroll down for one moment so I can read the last problem?
Oh, last problem.
Yeah, thank you.
Okay. Okay, so okay, now let's do an exercise computing determinants. Okay, um, so this is one of the important things, like one of the basic skills in this course. So okay, let me do a 4x4 determinant. Uh, okay, I'll not take shortcut. Let's do 1 2. Okay, I think this should not be 0. Okay, so the idea is you can pick your favorite row and then use that to expand. So I will just use the top row and um, do it. So also there are few properties. I don't want you to compute mindlessly. There are few properties that are always useful. That is determinant of A is A transpose. And then if you swap rows, then you have to add a minus sign and stuff. Mm, your determinant changes by some minus sign, and if you like swap like n rows, then it swaps by -1 to the n. I would have done this in class, but you know. And this is also there in the Karen Smith's notes as a homework, but you can use it if you like in the exam. Okay. So yeah, you can use all these row reduction sort of business, and then say that okay, we reduced row here, and these were the determinant of the row reduction matrices, so finally you can multiply with them. That also is fine. But uh, this we will just do it straightforward manner, so we'll expand it using this, and then for this we will forget this row, sorry, this column and this row, and then for this one we'll forget this column, and so on. So this is 1 times determinant of this 3x3 block, then minus 2 times determinant of this other block, 0 1 2 3 3 times determinant of 0 -1 1 -1 2 0, then 2 2 8, finally -4 times determinant of 0 -1 1 1 -1 3 2 0 3. So what usually happens is if you're considering the ijth element to expand your as like one of the factors in your expansion, then you should have -1 to the I plus j, then your aij, then your determinant of the respective like the complementary minor, and then you do it for if you are using the ith row, for example, then I runs from I is fixed, then j runs from 1 to n. This is how it works. So now here this is the first row, first column. So we just have -1 to the 1 plus 1. Therefore, this is positive 1. For 2, we have first row but second column. So -1 to the 1 plus 2, that is -1 to the 3, so that is negative. So therefore, this is the negative term. For 3, we have first row, third column. So -1 to the 1 plus 3, so that is -1 to the 4, so positive. And for 4, we have -1 to the 1 plus 4. This is the fourth term. So this is again -1 to the even, -1 to something odd. Therefore, it is just -1. So this term is negative. So that is why the signs are flipping. And why it is this is also um, like a, this is also not like a commandment or anything. Determinants happen to be alternating multilinear map from like Rn to R if you are computing n cross n determinant. So it takes n vectors from Rn and gives you a real number, and this multi and it is multilinear. So that is, if you fix any rest n minus 1 vectors, it is linear in each of the remaining components, and it is also alternating. So that is, if you swap columns, then the sign of the determinant changes. And that very thing also forces, if you have two same columns, then that would mean that the determinant is 0 and stuff. So from that sort of a thing, this sign of the thing comes up. But this is something you don't need to worry about now. But this is not a, the point is, this is not something just like a useless rule. Okay, now you can compute all this. So this would be a long computation. My God. -1 times, so this thing is 80. Then this is -8. And then this guy is plus 2 times just -3. This one is 0 and -1 times 8 minus 4, 2 times 3 minus 6. Then, so we did the first two terms. Now we are doing the third term. So determinant we are expanding in terms of like this manner. So the first one is 0. Then this is negative of -1, so +1 times 8 minus 4, and then 2 times, this is just 2. Plus 1 times 3 minus 6, and then plus 1 times positive 2. So we get, this guy is -18, this guy is +8 and -6. So -24 plus 8 would be -16. Then this is -4, this is -3, so -6, -4 is -10 times -2 is +20. This is 4 times 4, I mean 4 plus 4, 8 times 3, 24, This is negative 3 plus 2, so negative 1 times negative 4, so positive 4. So we get this is 48 minus 36, which is 30. What? 48 minus 16. So this is 32. Okay. Okay, but yeah. Now also, for example, you have a determinant that is a 4 cross 4 determinant, but suppose you have like 1 1 minus 1 7 or something, 0 0 0, and then 2 3 4 5 8 9 7 2 minus 1, something like this. So computing a determinant that looks like this is actually very easy. Why? Because if you see, if you try to expand it in terms of the, you can, if you want, you can change, swap the rows and columns, then this is then this is clear. Determinant of A and determinant of A transpose are the same, so there is no problem. If you still expand it just using the first row, okay, so let me write that down what I said. So suppose this is your A, okay, so A transpose is clearly 1 this and blah blah blah, okay. Now as soon as you see this, then that means you really have to just compute one thing, just this one and this determinant. So this is really computing a 3 cross 3 determinant in the end, right? So compute the determinant of A transpose and you are done. Or if you don't want to do the transpose, uh, I mean it is really the same thing, but the idea is that if you expand, then the expansion of this and this term will always have this 0 column in them, hence those determinants will be 0. So again you end up computing really just the determinant of this guy, this 3 cross 3 guy. Okay. So yeah, that's just one small point.
Um, can we not expand to like the column as well?
Can you not?
Like expand to the column as well?
Yeah, sure.
Oh, I guess it's the same thing.
Yeah, again same rule, minus 1 to the 1 I plus j, however you like.
Could you go a bit up, like to the previous? Okay.
Okay.
Yeah, thank you.
Okay, so the point is, so far, make sure that you understand the definition of characteristic polynomial, how to, and the, like, write the definition of eigenvalues, eigenvectors, and learn how to compute them given any 3 cross 3 matrix or any matrix for that matter. But in the end, if you are doing computation, I don't want to give a 4 cross 4 matrix and you have you spend all the time in that. Um, okay, so that's one, and then two is, um, this is the rule to compute determinants. So these are the two things we have done so far. Okay, then I guess we defined cross product. So yeah, now, um, so I think, I don't know if we proved this. I think we proved this in class. So if you have V, W, and U, so let me change the order. If we have U, V, and W, all of them 3 cross, this is a 3 cross 3 matrix. So computing the determinant of this guy is also same as just computing this, the dot product of U. So let me write it this way, with V cross W, and V cross W is in cross product. Again, remember, how does cross product work? Um, So we had this sort of bad looking formula that you take the determinant of this bit with some sign, and then for the second part you take the determinant of this bit, and then for the third part you take the determinant of this bit. That was the cross product thing. So using that one can explicitly prove this. Okay, good. Now, and we also did stuff that V cross W is orthogonal to V and W and stuff. So, continuing from here, if one gives you a matrix, whatever can be here, you have zeros, and then you have the U1, U2, U3, V1, V2, V3, and W1, W2, W3 here. So let's say this is 17, 29, 31, something like this. Then computing the determinant of this matrix is really again what? Computing the determinant of this matrix. And we know this is using this rule. This is inner product of U with V cross W. So if someone asks you to prove the determinant of this matrix is this, then that is actually a very simple problem, right? Do you agree?
Yeah.
Okay, good.
Yeah.
Okay. All right. So let's do some problems from the. I mean, if you have any questions, you can ask me, and I can go over those. But I think it's better if I do the problems from the practice midterm. Okay, so always you should know that I will always ask definitions of important things. So you should learn how to write those correctly. And okay, so then there are some nice things. Okay, so suppose S is some non-empty subset of Rn. Okay, then we said S perp are all the vectors in Rn such that V, this is a small s, is 0 for all small s in S. Okay, this is the set of the perp, S perp, like the orthogonal complement of S or whatever. So I think it was a homework that L of S is orthogonal to S perp. So let me just prove that. Okay, so L of S is just elements like this, say alpha I, I from 1 to k. Let's call this thing something S tilde. Okay, okay. So for V in SPURP, you know that V S tilde would be V alpha ISI 1 to K. So that is alpha I VSI 1 to K. So VSI by the definition of SPURP are 0, right? So this guy is 0. So right. So we picked any element of SPURP and we showed that we picked an arbitrary element of LS and then we showed that it is orthogonal to all the elements of V. So thus do the other thing. Showed that L of S is SPURPs. SPURP. Right, this is what we did. And then the other way, we want to show that yeah, I mean that proves it. We want to show that LS is orthogonal to SPURP. So we did that. Now I actually think that LS is actually equal to SPURP. That should be true. Yeah, that is true. Okay, so let's try to do this other way. Pick some V in SPURP. Then okay, this is true, but the way I'm trying to do it is not going to be easy. So let's do what I want to do. This is not this. Okay, whatever. Yeah, so what I want to do is L of S direct sum S part. I want to show that it is Rn. Okay, so to do this, this is called the direct sum. Right? So direct sum consists of two things that we have to show that LS plus S part is all of Rn and LS intersection S part is trivial. Okay, so this guy is actually easy. So if you just pick some V from LS intersection S part. So because V is in LS, you can write it as some alpha I SI 1 to K. Then but V is also inside S part. So V with V is V with sum over alpha I S I. That means this is alpha I V S I. But the fact that V is in a SPURP makes all these terms 0, therefore it is 0. So that means you have proved that norm of V squared, that the length of V squared is 0. But the property of length is such that the length of a vector is 0 if and only if the vector itself is 0. Right? So that means we proved that this guy is a subset of 0. And 0 is always a subset of that intersection of any two subspaces. So this is trivial. Okay, so that is fine. We want to do the other thing, that the plus thing. All right. So for that, pick any vector from Rn. So ls plus sperp is always a subset of Rn because you know the definition of plus. These are all possible finite sums of any two elements of these two. Well, really any finitely many elements of these two subspaces. We are just taking all possible linear combinations essentially. So that would be a subspace of Rn because ls and sperp are subspaces of Rn to begin with. So this inclusion Rn, this is obvious, right? Nothing much to do there. So it is the other way that requires some work. Okay. So to do this, pick an element V from Rn, right? Now, what we would do is um, we would find a basis for ls, like the linear subspace spanned by S, and then um, write V in terms of that, and then basically um, yeah. So what we want is to okay. So okay. So let me give you what this really geometrically means. So when you want to do this, so these two things combined means that you want to write each vector in Rn uniquely in terms of ls and sparp. So that is, given a vector v, you are decomposing it essentially in two parts, say v1 and v2, or rather w1, such that v1 stays inside some subspace and this guy becomes orthogonal to that subspace. So all you do is you choose some basis for your subspace and then look at the projection of all the vector along the basis directions and then subtract those off. So if you do that, then if you subtract those things off, then what remains would have to be orthogonal to this subspace to begin with. So that is the basic idea. So suppose for now that S is, it doesn't uh, create any problem. Suppose S is just two elements. Okay? So I'll just assume that S is just two elements and then do this. So the projection of V along S1. So okay, S is two elements and then suppose L of S that is also two dimensional. So suppose this is just two vectors. These are two basis vectors. Suppose this is v1 and Okay, I need to choose some other. Okay, u1 and u2. Okay, suppose u1 and u2 is the basis for ls. Okay, so oh no, I forgot to record the lecture. Okay, sorry. I will just record the last 11 minutes. Okay. Right. So suppose u1 and u2 are two uh, u1 and u2 is like are two elements in the basis of S. Okay. It doesn't have to be two-dimensional. You can do it for anything, but yeah, I just don't want to do a lot of details. Okay. So we are given some V in Rn. So we are sort of trying to subtract off the projections. This is the projection of V on U, U1, and this is the projection of V on U2. And before doing that, before doing this thing, we will try to make U1 and U2 orthogonal to one another. Okay, if you have a two-dimensional space, you can find a basis that is orthogonal to one another. So you can start with any basis. How do you do that? You can start with any basis U1, U2, and then you can make the U2 guy again just subtract of the projection. So let's define U2 hat U1 minus U1 U2 norm U2 square U2. So if you define U2 hat to be this new thing, subtracting of the projection of U1 from it, then sorry, I didn't want to do this. I want to do U2 minus U1, subtracting of the projection of U1 from U2. This is U1 square. Okay, so if you now compute the dot product, you can see that these two guys are orthogonal to one another, because if you apply u1, so we are taking dot product with u1 here, right? So then this is u1 u2 minus this is norm u1 square and this also becomes norm u1 square. So what is this stuff? Okay, so this and this cancels, and then this is 0. So this guy is so u2 hat and u1 are orthogonal. Okay, so we start with one such basis, and then for that basis, along that basis, I mean, you can understand this geometrically also. If this basis doesn't have is not like orthogonal to one another, then once I start subtracting just like the components, you either will like add some extra, like by subtracting this and this, we'll either add some extra components to one of those things or subtract too much, and then it will not be um, yeah, we'll not get what we want. So we start with clear things. We start with a basis that is orthogonal, And along those orthogonal things, we look at the components of any given vector and then subtract those off and make that that will make it like the ortho that will like the, whatever remains is orthogonal to that entire subspace. So now let's check that. So my claim is that V minus this projection thing V minus sorry this projection thing, this is U1, okay, this is U2 hat square. This guy would be orthogonal to LS because LS is spanned with this. Okay, is orthogonal to L of S. Okay, so pick any vector W from L of S, right? Then W looks like some, well, we have two basis vectors. So some alpha 1 U1 alpha 2 U2 hat, right? Okay, let me call this thing V tilde. So now we want to show that W V tilde is 0, right? So W is alpha 1 U1 alpha 2 U2 hat, and then we have V tilde. So this is alpha 1 U1 V tilde alpha 2 U2 hat V tilde. Now U1 V tilde and U2 hat V tilde we can compute separately. So U1 V tilde is U1 V minus VU1 and square U1 minus VU2 hat square 2 hat. So you know that a dot product is like bilinear. So if you fix one of the components, then it is linear on the other. So we are fixing the U1 component, so it is linear on the second component. U1 is this one. Okay. So then we get U1 comma V minus VU1 by norm U1 square. So U1 and U1, so this is a scalar, right? This is a dot product which is a real number. This is some norm. This is also a real number. So this is really the vector. So this is U1 dot U1. So that is the length of U1. And then this other guy is V U2 hat by norm U2 hat square, and then U2 hat U1 or U1 U2 hat. Dot product is commutative, it doesn't matter. So this we started with an orthogonal basis, therefore it is 0. And this is the only reason we wanted to make it orthogonal, so that I can make it 0. This and this cancels because they are the same and non-zero, right? U1 is a non-zero vector. Therefore, we are left with VU1 minus U1V, which is just the same thing. So this is 0. So U1 is orthogonal to V tilde. Similarly, you can show that U2 hat is orthogonal to V tilde. U2 hat V tilde is also 0. So that means this is alpha 1 times 0 plus alpha 2 times 0. This is just 0. So for any element in LS, we have shown that it is orthogonal to that. So this vector is orthogonal to that. So therefore, and you can see that U1 and U2, this part is already in LS. So this is V U1 norm U1 square U1. Okay, Let me erase some stuff. So v u2 hat norm u2 hat square u2 plus this v tilde guy. V tilde is this. Okay, this part is orthogonal to ls, so is in spark, and this part is in ls, right? So we did prove that ls and spark gives a direct sum decomposition on of Rn. Okay,
Uh, can you please like briefly like go over again, because I think
yeah, sorry. Sure. Yeah, so we are trying to prove this. This is one of the problems in your, like, there are like 2 3 problems that combines to this thing, that uh, if you have some non-empty set, if you look at the orthogonal complement of it, and if you look at the linear span of it, they can decompose your space into 2 orthogonal subspaces. Okay, that's what the sign means, that the sum is all of Rn, and the intersection of these 2 subspaces is just the trivial 0 vector.
Mhm.
Okay, so this is the definition of direct sum. These 2 conditions are the definition of direct sum. When these 2 things happen, we write this plus dot. This is big O plus in LaTeX. This is called well, this is called direct sum. I don't know what it's called.
Okay.
Okay, so we want to, so we are proving the second thing. This is actually easy. You just, that is here. Pick some non-trivial element from the intersection.
Yeah.
I mean, pick some element from the intersection. So because it is in ls, linear span of S, it must look like this, right? Alpha I Si, Si are elements of S.
Yeah.
Okay. So if we compute the norm v comma v, so in one of the v's I am writing it as alpha I Si. Okay.
Mhm.
And the other v is the same v, right? We're writing the same guy, like just 2 different identities of them. So this S perp, since v is in S perp, if I apply this v to this thing, so again use linearity, fix the v, so alpha is comes out, come out, and then you have vsi, sum over alpha I vsi. Now this v, because it is in S perp, if you take dot product of it with si, you'll get 0. So
Yeah.
each term here is 0. So this is 0. So therefore, you prove that the v that you picked here, that actually has 0 length. Okay, but what vector can have 0 length other than the 0 vector? Therefore, it is just the 0 vector, right?
Mhm.
So
Yeah.
that proves the second thing. Now we are into proving the first thing, that ls sum is perp is Rn. So what is the sum operation? We did this in, I guess, the previous midterm, that you pick, uh, so v plus w is like you pick elements from the 2 spaces and take their sum. This turns out to be a linear subspace, and this is the smallest linear subspace that contains both v and w and stuff. Anyway, so so that is what we want to prove. We want to show that ls plus s per is Rn. That is, we'll pick any element from Rn, right? And we will write it explicitly as, so we'll just, so pick a v, and we will write this as some element of ls and some element of s per. So we will have v1 and v2 such that v is equals to v1 plus v2, where v1 is in ls and v2 is in s per. Okay, so the class is done. If you have to go somewhere, you can go, but I'll just explain this. Okay, so that is the task. Now, since both ls and sparp are linear subspaces of Rn, their sum is also a subspace of Rn. So one side of the inclusion is trivial, that ls plus sparp is a subset of Rn. That is obvious.
Yeah.
The real thing is to do the other way. Pick an element from Rn and show that it is here. Okay, so to do that, we are starting with, so we don't know what is the dimension of ls. We actually don't need to know, but I so what we need is an orthogonal basis for ls. Okay, for what I am doing. So the idea is simple. You want to make two things orthogonal to one another. You have a v, right? Then if you have nice enough components for your subspace, so you have a v, and then so for that v you want to know what is the orthogonal, like what part of the v is orthogonal to some given subspace, right? That is the task. If you know that, so you can, for example, you can choose a basis for ls, right? And extend the basis to the basis of rn, right? So
Mhm.
whatever v you pick here, that will have some part of it will come from the basis that spans ls. Okay, so it is the remaining part. So to make the remaining, like the remaining basis orthogonal to ls is the real, like the only thing that we need to do here. Okay.
Oh, okay.
Okay, yeah, so for that we are starting with a basis of ls that is the orthogonal basis.
Mhm.
Okay, now pick any vector v from rn. Okay, every, so you, if you are given a linearly independent set, you can make it an orthogonal set. We will do this as an algorithm later in the, after the midterm. Okay, so we start with some orthogonal basis and we consider v. Then all we are doing is that we are looking at v and we are looking how v projects to this basis vector, how v projects to this basis vector. Okay, and then what we will do is we will just delete those projections. Then what will happen is v will have no projection along u1, v will have no projection along u2, therefore v will have no projection along the subspace spanned by u1 and u2. So v
Oh,
would be just completely orthogonal to the subspace. That is the geometric idea behind this algebra.
okay.
Okay,
Okay.
yeah, so that's all we do. So this is the projection of v along u1, this is the projection of v along u2, and then we just subtracted it off. This is the v tilde. Okay, then
Oh,
we prove, then we basically showed that this v tilde is actually orthogonal to all elements of ls.
hmm.
Okay, this got
Okay, I
erased for
got it.
some reason. Yeah, okay,
Thank you.
yeah, no worries.
Uh,
Okay,
excuse me.
yes.
Uh, so I think if the intersection of the linear span of S and S perp, the intersection is only the zero vector. So any vector v in Rn is either in the linear span of S or in S perp or in both, which is zero. So I think so there are maybe three cases. One, it is v is the zero vector, which which makes which means v is the sum of zero vector and zero vector, and both zero vectors, one in L of S and one in S perp. And the second case, if v is in the linear span of S, then v could be written as maybe the basis of S, linear combinations of basis of S plus linear combinations of basis of S perp using all coefficients are zero. So the third case, v is in S perp and not in S, then it's similar. So it's a zero vector in LS plus the linear combination of basis of S perp. Could I write like this?
There is a subtle problem with your argument. So what you are trying to say is, if I understood it correctly, it is like this. So what you're trying to say, think about this geometrically inside R2. Okay.
Okay.
So in R2 you have the x-axis and the y-axis, right?
Yes.
Then if you have any vector w, so you can have a vector w, right? That is neither in this
Right.
nor in this, but it has components in both, no?
Oh, yes.
Right?
Yes.
Yeah. So what we are doing, we are not making w a new vector. So w has lot of projection along lot of things. So we are finding a projection of w that becomes perpendicular to this y-axis. I mean, because we know x and y axis so well, it is misleading. So let me use some other example. So suppose you have this line x equals to minus y and x equals to y, right?
Right.
They, okay, something's happening. Anyway, so they perfectly span the all of R2. This is a basis, right? This 1 comma 1 is a basis. 1 comma 1 and 1 comma minus 1, it is a basis. So pick any w, right? However it looks, x, y. Then what our task is to find a component of xy that is just like we want to write this xy guy as some vector plus some other vector such that this vector is orthogonal to this line.
Oh,
Okay, it
yeah.
doesn't mean that the vector itself is just this part or the vector itself is just this part. It
Oh,
can have components. Okay, but the
oh,
task is we want to make one of the components orthogonal to some given subspace. So in that case, all we need is that the given subspace. So we need to start with some orthogonal basis of that given subspace. Once we have that, then we can project this vector along those bases, right? Along each of those orthogonal bases, and then subtract off those projections.
oh, yeah.
Okay. So yeah,
So it's the Gram-Smith process, right?
yeah, it is the Gram-Smith process, but it is. I don't want you to go by just names. Okay, understand the geometric idea behind it. This is
Oh,
some physics sort of stuff you did, I guess, in at least in India we did in class 11 or something. So this is some vector, okay, and this is
okay.
one component of the vector and the other component of the vector. This is the x component, y component. Now all we are doing here, we want to, so say we want to find some component of this that is orthogonal to it. So orthogonal to this span line spanned by this thing. So just subtract, if we just subtract of this projection from this vector, then what remains is just this guy, right?
Right.
And this guy is orthogonal to it. So it is the same picture in higher dimensions. You have some subspace and you have some vector. So you have lot of components because it's some n dimensional vector, lot of components in a lot of directions. Now consider some orthogonal set that spans like orthogonal basis of your subspace that you which you want to make like which you want to make it perpendicular to, right?
Right.
Now look at the projection of this vector. So now since this is an orthogonal set, if you had like really look at those components of your vector, then it would have some projections along each of these things. Now if we just subtract of all these things, it will not have any components along this subspace. Only remaining components would be some other directions, right?
Yes.
That is the thing that we are doing here. So,
Okay, thank you.
yeah, no worries. Okay, cool.
Thank you, Professor.
Yeah, okay, thank you.
Okay, thank you so much. Goodbye.
Yeah, no worries. Bye.